In this video, we'll look at a range of issues that might be present in the design of a database, why those issues might pose certain problems, and how to approach resolving those issues using a method called normalization. We will start by defining three types of dependencies in relational databases. Then we will look at a range of problems that might be present in the design of a relational database. And we will continue exploring how normalization can resolve those problems. Specifically, we will look at three types of dependencies: functional dependency, partial dependency, and transitive dependency. The first one, functional dependency, is the kind that we would want to see in a relational database. That's the good kind. The other two, partial and transitive dependencies, are the bad kind. Those are dependencies that we don't want to see in a relational database. And whenever we see them, we try to resolve them, we try to remove them using normalization. To use a formal definition, a functional dependency is present whenever the values of an attribute y depend on the values of another attribute x. In more practical terms, a functional dependency is present whenever we're able to identify or determine the values of an attribute if we're given the values of another attribute. A good example to that would be a non-key column that depends on the primary key column of a given table. For example, in a student's table like this one, the values of the first name column would depend on the values of the primary key column, student ID. Which means if we're given a student ID value, we can determine the value of the first name attribute. Hence we say the non-key column first name is functionally dependent on the primary key column student ID. As a rule, in a completely normalized table, any non-primary key attribute should be functionally dependent on the primary key and only on the primary key. If the primary key is composite, meaning it consists of two or more columns, the non-primary key attribute should be functionally dependent on the whole primary key. Here's a phrase you can use to remember the rules around functional dependency in a relational database. Any non-primary key attribute should depend on the primary key, the whole primary key, and nothing but the primary key. As we will see later in this video, normalization is a method we can use to ensure that these rules hold for a given relational database. Now let's take a look at the two unwanted kinds of dependencies. If a non-primary key column y depends on not the whole composite primary key, but only a subset of the fields that make up the primary key, then that column y is said to be partially dependent on the primary key. Note that this can only happen in a table that has a primary key that consists of two or more columns. For example, in this line items table, the primary key consists of two columns, order ID and item ID. There are two non-primary key columns in this sample table, quantity and customer ID. The quantity column is functionally dependent on the whole primary key, because in order to be able to identify the value of the quantity column, you need to know both the order ID and the item ID values. Meanwhile, customer ID is partially dependent on the primary key because it only depends on the order ID values. If you're given an order ID value, you don't need to know the items on the given order to be able to tell which customer placed that order. That means customer ID values depend only on the order ID values, and hence customer ID is partially dependent on the primary key. A transitive dependency is present if a non-primary key column y does not depend only on the primary key, but also on some other non-primary key column. That means if we can tell the value of a non-primary key column y when we know the value of another non-primary key column in the same table, then y is said to be transitively dependent on the primary key. That also is another problem, and it needs to be resolved through normalization. For example, in this orders table, the customer name column doesn't directly depend on the order ID column. It depends on the customer ID column, which in turn depends on the order ID column, which is the primary key field for this table. That means as long as we know the customer ID value, we don't need to know the order ID value to be able to know the customer name. Just by using customer ID, we can identify the customer name value. That means the customer name column is transitively dependent on the order ID column, and this is a transitive dependency and needs to be resolved through normalization. There are other problems we can encounter in a relational database that go beyond the dependency issues. The two important problems that are pretty common are non-atomic attributes and multi-valued attributes. Non-atomic attributes are attributes that are not divided into their smallest meaningful pieces. For example, in this table, the customer name and customer address columns are non-atomic, and they must be divided into their atomic parts so as to hold the smallest meaningful pieces of information. The customer name column must be divided into first name and last name, and the customer address column must be divided into street address, city, state, and zip. Multi-valued attributes are attributes that hold more than one instance of a type of value in a single record. For example, in this table, the team members field is a multi-valued attribute since it holds multiple name instances per record or per row, and it must be divided into subfields, each of which will hold only one value or one name. Note that this would lead to another issue, repeating columns. Repeating columns are problematic because they may lead to many null values. Imagine many of the teams listed in this table having fewer than 4 members. That would lead to null values in the member 4 column. Repeating columns may also require changing the structure of the table over time. Imagine future teams that have more than 4 members. That would require adding further columns to store the names of the 5th or the 6th or the nth member, thus changing the structure of the table over time, which is something we prefer to avoid as much as possible. Normalization is a method that we can use to avoid or to eliminate these and other potential problems in a relational database. Specifically, normalization allows us to avoid issues such as duplication of data, insert anomaly, delete anomaly, update anomaly, and partial and transitive dependencies in multi-valued or repeating columns as we discussed earlier. Here's an example to duplication of data. By keeping the customer name values in the orders table, we need to duplicate the customer name entries unnecessarily. Note that the customer name column in this instance poses a transitive dependency. Such a structure may waste resources and may lead to data inconsistency. Insert anomaly is present when, to insert an instance of an entity, you need to insert an instance of another entity first. For example, if you do not have a separate customers table and keep customer data in the orders table, you will need to insert an order first to be able to insert a new customer. If a new customer has not placed an order yet, you will need to insert a dummy order record. Delete anomaly is present if deleting an instance of an entity leads to an unwanted deletion of an instance of another entity. For example, if you do not have a separate customers table and keep customer data in the orders table and delete the only order placed by a given customer, that customer record will also need to be deleted. Update anomaly is present if changing the value of an instance of an entity requires multiple similar changes. For example, if you do not have a separate customers table and need to update some detail about a customer, like their phone number, in the orders table, you will need to update that detail on multiple order instances, assuming that that customer placed multiple orders over time.